Hello, so today we're gonna learn a whole lot about the sequence sine of n being natural number, and its subsequences. So the first thing that pops to mind is the oscillations of the sine function that keep happening until infinity, and therefore we don't expect sine of n itself to have a limit. And that is actually correct, and we will see a rigorous proof of that fact as well throughout this discussion. So 1, 2, 3, and pi is 3.14 something. So 3 happens just before pi, and the sine values, of course, are along the curve. And you again see the different y values that it takes in the positives and negatives similarly. But actually to get into the details of what is happening with the sine n function, I am going to forget about the Cartesian coordinate system, and I'm going to only focus on the unit circle. And to me, n will represent n radians. So here is what I do. I start at 0, and 1 means travel 1 radian along the perimeter. And recall that radian is nothing but the length of the arc that you travel. So I'll go counterclockwise to 1. I travel 1 more unit along the perimeter to get to 2, 3 again just before pi, and then there will be 4, and I will keep traveling counterclockwise. Now, my claim is these points form a dense subset of circle S1. And by dense, I mean every point of the circle you pick, either you will hit it with one of these points, or in any neighborhood of that point, there will be infinitely many of them happening. Yet another characterization is that you can always find subsequences that converge to any point that you fix. So how do I prove this claim? What I do is I first of all know 2 points will coincide on the circle. In other words, if after some rotations this is some n, and then this n will never be hit again by these points. That is, so to prove of this, suppose, so I'm proving this little claim here, suppose n is not equal to m, and without loss of generality, that m is strictly bigger than n, and m and n land on the same point on S1. This would mean that you were at n and you continued with some more rotations, and after some few rotations you came back to the same exact point that you were before. This would mean, so on the one hand, you've traveled an integer many 1 radians, because from n to m, you have made m minus n hops of 1 radian. So when you come back to the same point, you've traveled an integer multiple of 1 radian. And on the other hand, you don't know how many rotations around the circle you make and come back to the same point, maybe in the first one, or maybe after 1 million times going around the circle, finally m lands on n. But whatever the case, you have traveled integer many 2 pi's. So every time you make a complete rotation, you travel 2 pi radians. So you were at n and you did some rotations and you came back to n again after some time. So you've made k many rotations, complete rotations. So k many 2 pi's. This would mean, so for some k, you travel m minus n radians, which coincides with traveling k many times 2 pi. And this would mean that pi is m minus n divided by 2k, and that is contradiction because pi is not a rational number. So this proves then that no 2 points will coincide. So after traveling even infinitely many of these dots, you will never land back at 1 radian again. So this set of points is an infinite set inside compact S1. So we notice that S1 is a compact set. Therefore, for every delta positive, there exists 2 points that are at most delta distant in the units of radians along the arcs. So that's because you have infinite set within a compact set, there is some limit point, and from that you can see that around that limit point you take a half delta neighborhood, and at least 2 points, in fact infinitely many points, will fall within it because it's a limit point, but you only need to know that 2 points exist there. So let's go back to the picture again. Suppose that this is one of the points and this one is another one, and I assume they are pretty close, but to be able to draw nice pictures, I kind of am happy with this much. So this is the delta length. You know that some integer lands here and some other integer lands within delta. Suppose that this is the nth number. So xn is just n, but drawn along the circle, and this is xm. And again, without loss of generality, suppose xm is bigger, m, the index m, comes later, so m is bigger than n. What this then means is that m minus n jumps of 1 radian shifts xn by less than delta much to this xm. Right, so how do you get from xn to xm? By making 1 radian jumps and exactly m minus n many jumps. And we know from the assumptions that xm is delta close to xn. But if we now do the same from point xm, if you make m many jumps, if we make m minus n many jumps beginning from xm, then we will land exactly equal to previous amount, but let's actually be content with the fact that we will land delta. So I kind of don't want to. So suppose that this is actually equal to delta, so their distance, not just less than delta. We can always rename delta to the precise difference that they have along the arc. So here, so it shifts xn delta much to xm, and delta being small. So if we make xm minus n many jumps again, beginning from xm, you will land with another point, exact same distance, shifted in the same orientation. And you will land here. And then you make, so then you will land delta away from xm. And then if we repeat this process, repeat it, we will travel the perimeter by step size of delta. So all of this because of the symmetry in the circle. So if m minus n many jumps gets you from xn to xm, exact same number of jumps will push you exact same amount forward, because there's nothing about the starting point because of the symmetry of the circle. It all matters how many jumps you make and what effect it has on the initial point. So if you keep doing m minus n jumps, they will travel along the circle with a step size of delta. So this would mean then, therefore, in a delta neighborhood of any point on circle, there does exist some xn. So again, back to this picture, if you give me any point now, and I take delta neighborhood of that, so I move delta this way and delta that way, one of these points will land there, right? Because if there were no points, that would mean you have skipped by a step size of 2 delta, which isn't the case. And now because delta can be chosen arbitrarily small, because delta can be chosen arbitrarily small, this proves density. This proves density of the set xn's in 1 to infinity. So maybe notation can be improved, but the geometry is there, so you shouldn't be struggling with convincing yourself why we can travel at any small step size that we wish. So ultimately, you have proven that in any delta length of arc, there do exist some of these integer points. And this delta can be chosen arbitrarily small, so these points are everywhere at every scale. And that proves density. Now we can prove a lot of corollaries from this. So for instance, for every alpha between -1, 1, there exists a sequence of natural numbers, say n1, n2, n3, such that limit of sine of nk, k goes to infinity, is that alpha. So how do you prove this? What you do first is you find the right angle which gives you the alpha sign. So here is alpha, so you find the right point, so you take this to be some beta. So proof, find a beta such that sine of beta equals this alpha that you are given. Then by density above, there exists this sequence that we are seeking such that these points which we showed, so when you put these integers on the circle, we denoted them by x subscript something. So here will be, say, x of n1, here will be x of n2, and maybe here is x of n3. But with density, we've chosen these so that x of nk converges to beta as k goes to infinity. And because sine is a continuous function, so sine of xnk then equals sine of beta. But this guy here is just sine of nk. So here I'm kind of cheating. I'm using x and k to represent the corresponding angle to nk on the circle. So we know that nks themselves do not converge to anything. This is a sequence of natural numbers, so there's at least a gap of 1 between them. So they do not converge anywhere. What converges, though, is when I place them on the circle. You can also think about this as taking mod 2 pi. That means you bring all these integers back to the interval 0 to 2 pi. So because you can subtract any multiple of 2 pi without changing the sign quantity, so you bring a copy of n2 back here, a copy of n3 back into the same interval. This is much better represented on the circle. So if you represent these n1, n2, n3, n4 on the circle, now they do converge somewhere. And here it converges to this beta, so their sine converges sine of beta, which is equal to alpha. And that ends the proof of this particular corollary. So it's interesting. That means the values that sine of natural numbers take is basically every number that sine can take. We know sine is never outside this interval. If you go back to the Cartesian picture, this is saying that fix any number between -1 and 1. Give me any number here, and I can find the right integers so that the sine value of these converges to that. So although sine can do its oscillations, these points are such picked, maybe this picture really isn't accurate, but these integer values are can be such picked. So here, for instance, maybe back here you have this integer. So this is like n2, this is maybe n3, and here is n1. So these integers can be picked in such a way that their sine, the height at those points, these dots actually approach to the height of alpha. So that's one amazing application of this density there. Another application is that you can estimate multiples of pi by integers. So corollary 2 is for every epsilon positive, there exists n in natural numbers and there exists m in natural numbers such that n pi minus m is less than epsilon. So proof of this one can be done this way. So again, you want to represent m by some jumps of 1 radian along the circle. So again, my picture is not as good as I wished it would be. So here is 1, here is 2, here is 3, and so on. We know that this pi is also in the limit set of these integers. Because these integers are dense, in particular, you can estimate this point by such integers. So that means for every epsilon, one of these points, maybe x of 300, will land pretty close to that. So epsilon close, you take this epsilon error tolerance, and you know that some of these points ultimately will land there. So this will be your x of m. And on the other hand, you can count how many times you've actually rotated along the circle when this happens. So you keep track of how many 1 jumps you have, and at the same time you keep track of how many 2 pi rotations you've had. And that the fact that these now are pretty close points is exactly saying that some multiple of 2 pi, or you can put this 2 inside the integer, so some multiple of pi is pretty close to some multiple of 1 radian. And that's just so this is a pictorial proof, but I think it's good enough. Let's see that why this isn't actually an easy result here. You can say, well, I can approximate any pi by any rational number, right? Because rationals are dense inside real lines. So this can be made as tiny as I wish. and then I multiply by n pi to get, and then oops, you have no idea how big this can get. So the only way around it would be to make sure that this epsilon is, say, less than n squared, for instance, so that even after multiplying by n, you still have 1 over n. But we don't know, simply because rationals are dense in the real line, that such approximations are possible. And there's some interesting number theoretical stuff regarding this, like approximations, where you say much more than simply saying rationals are dense in something, which I have no expertise in. So hopefully you enjoyed this treatment of the sign of natural numbers. The takeaways are natural numbers become dense on the circle if you rotate, and therefore their sign values become dense in the interval -1 to +1. So if you liked the video today, please like the video, and if you have any questions, please comment. Hope to see you in a near future.